Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. And as you step on inside, we will review 3.1 to 3.3 of the Integrated Math 2 Big Ideas Math textbook, where we were graphing out of y equals ax squared, y equals ax squared plus c, and y equals ax squared plus bx plus c. Running the whole gamut of things in standard form, whether we are translating vertically, horizontally, or not at all. And we have to sometimes find vertex in different ways. Really, the end result is they are in standard form, some with less translations than others. If you recognize that, great. I wouldn't treat them as different sections entirely. But once again, if you recognize that there's no B term, then we're only moving up and down. If there is a B term, we get to move left and right in some sort of way where we find the vertex using negative b over 2a. Oh, a whole bunch of things we get to cover. But if it's just ax squared, there are no translations. Vertex at the origin, axis of symmetry, x equals 0. Yep, if all this connects well, then doing the problem should be a breeze. Numbers 1 through 23, I'll take a look with you at the for the first time right now. I might have to pull up the calculator later if they ask us to do certain kinds of questions for that, and I'll pull up graph axes if we ever need them. So let's go ahead and get started. Let's take a look at number 1 and 2, where we identify characteristics of the quadratic function and its graph. So let's see. I'm going to draw on this side, I suppose, for now. When it comes to that, I can't remember everything they asked for specifically. I know that there was vertex, domain and range, axis of symmetry. There might have been y-intercepts, x-intercepts. I can't remember specifically what. But let's go ahead and look at some of these guys here. Let's refer to the vertex to begin with. And I promise to write all the stuff on the other end as well. But the vertex is at 1, 4, like that. And then we have the axis of symmetry as well, this dotted line that goes through there because these parabolas are symmetrical. And then we have this y-intercept. You know what? I'm going to keep the vertex hidden for now. But that's the vertex. And then we have, give me 1 second, trying to locate a pen. We have the y-intercept right here. And I don't think they're going to ask about x-intercepts there. That's a solving thing for later, but there's that. Here's the axis of symmetry, like I said. And domain and range we'll get into after that. But that's kind of where we're going. And I don't know, I guess it has a maximum. I guess we'll refer to that as well. All right, so for number 1, with all that stuff in mind, guys, we have a vertex at 1, 4, like I said. Yeah, I'll go and say the maximum, or well, hold on, axis of symmetry. Axis of symmetry at x equals 1. It's going to be the same as the h. It's that vertical line that goes through there. There is a maximum value of 4, right? That's the y value. There's a max of 4, and that helps you understand your range as well. Y-intercept at 0, 3, and your domain is all real numbers, and your range is y is less than or equal to 4. I hope those were the only things that we kind of put within there, and hopefully it's making sense what it is. I don't know how much I can teach and explain with that other than the vertex shows the axis of symmetry and your maximum or minimum, all given that. Let's move on to number 2. I believe that's it. Now, these features, just pay attention to the scale. All the stuff will be the same when it comes to vertical lines and stuff like that, so I'm not going to draw on it this time, but pay attention to the scale. These are looking like they go by 2s. So when it comes to the vertex, it's at -2, comma, what's between 4 and 6 is 5. So -2, 5. The axis of symmetry will be at x equals -2, that vertical line that would have gone right through the vertex, right through the middle. This has a minimum this time as the graph faces upward. It has a minimum of 5 for the y. It's the y represents the minimum. Minimum of 5. The y-intercept, I guess it's crossing through 4, 6, 8, 9. Y-intercept of, I'm just going to put 9. I'm just going to put the number. Y-intercept of 3, y-intercept of 9. I don't know if they referred to y-intercepts yet at the time of these. I don't even know what section. 3.1? They might have referred to it. I don't know. The domain is all real numbers once again. The range is y is greater than or equal to 5. So I hope those were all the things that they covered. Vertical stretches? Did they? Maybe they mentioned all those other things. Maybe they mentioned like reflect over x-axis. I don't know. That's transformation. No, that's for later. All right, I'm going to leave it as that for now. Hopefully that's going to be enough for us. Sorry about this. Kind of my on the fly stuff. Numbers 3 through 8, we're going to graph these functions, and we will compare them to the graph of f of x equals x squared. I learned my lesson from previous things, and I'm just going to use the tall graphs only. So let's copy and paste that in for each problem. So these ones, I'm going to plot as many points as I can fit, whether or not that seems appropriate for what you have. I'll attach this online as a PDF, as always. H of x equals negative x squared. We are comparing it to f of x equals x squared. Keep that in mind. So x squared, are we doing both? Graph the function compared to this. Well, I'm going to graph this once, x squared, where it looks like this. When you go over a certain amount, you go up the squared amount of that. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and same is true of the negative values. So this is positive x squared right here. This is your f of x graph that we're going to compare these things to. So, okay, I suppose I can keep it up there for all the things that we do. So I'll make sure to copy and paste that. We'll put it down below for future reference. Boom, I got that one in place for number 4. Okay, h of x equals negative x squared. Now the negative also means that your a value is negative 1, which does mean it is a reflection over the x-axis. So instead of being up like this, it's literally just going to flip over. It's going to look down like this and really be identical otherwise. There's no stretch, but there is a reflection, and that's what we're looking at right here. Now, these points are also reflected across the axis of symmetry, that is x equals 0. And that didn't change at all. There was no translation of this one. This is very much a 3.1 section thing. These might go in order. The first ones apparently were from section 3.1 to list some features, and that's what that is right there. So here's h of x. Here was f of x. I'll make sure to include that on the future problem. But they asked you to describe the transformations. There's only one transformation that's occurring here, which is reflection over the x-axis. Reflect over x-axis. And that is number 3. Number 4. P of x equals 2x squared plus 2. Okay. P of x equals 2x squared plus 2. So the original graph, as you see, is what it is. We're going to graph the next one in blue. Now the plus 2 represents a vertical translation. We are moving up 2 units on this guy right here, and that's where the vertex would be located. Now beforehand, technically there was a vertical stretch. Let me actually, you know what, I'll speak on the vertical stretch first. This 2, the a value of 2 represents a vertical stretch. And there's a c value of 2, which again is a vertical translation. But let's talk about the vertical stretch first, because that's what happens first, right? You square your value, and then you multiply it by 2. So vertical stretch. So we take that guy there, and we make this one 2 times taller. Instead of 1, that's 2. Instead of 4, this guy's 8. Instead of 9, this guy's at 18, which would be technically past the graph here. So these, all together, make their own parabola, like this. And you'll have to bear with me when I do the translation. This is hard to copy and paste. And by the way, don't draw this yet. Don't start just copying what I draw, please, because I'm about to do something to this thing. Yes, I am. First of all, I'm going to hide it. Not intentionally. I just got to get some things done. I got to hide it in the background of this other thing so I can grab the points with it. Okay, so let's see if I can grab all these points. Boom, 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 boom. Okay, what I'm about to do is I'm about to vertically translate this guy right here, okay? Everything's going to go 2 units upward. So you double all your values in height, and now this goes upward like that. So this is what I would have done to begin with, I suppose, on the problem. Generally, I'm going to start with the vertex and say everything I do is in relation to the vertex. But now that I move those up, this is where the new points are. So now instead, this thing is at 10 right there, and this is at 4, and all that kind of stuff. So everything moves up like that. Excuse me. This was a vertical stretch by a factor of 2. And then we translate it up 2 units. Okay. Give me 1 sec. I got an important email I got to respond to. Okay, we are back. All right. Yeah, so that's the result. So what I'm going to do in the future on those problems, when I think this is ax squared plus c, this is now out of section 3.2, technically from this one, is that this was translated 2 units up, and everything else translates 2 units up with it. If you saw me move every piece, I said we doubled them, sure, but everything moves up. So if I move everything up first, then I'm going to talk about, all right, from here, when we go over 1, let's do this and double it. Not the y value, but the distance from the vertex. So if I do things in relation to the vertex, things should be pretty hunky-dory there. So let's go ahead and move on to copy and paste that guy. And then let's move on to number 5, where I'm going to keep doing the same thing. Remember, this is the original f of x. I just keep this here for good measure. I don't think you're necessarily required to graph that one. In fact, I think I should stop. Yeah, let me get rid of it. All right, you know what that one looks like in the concept. Actually, let me remind you. 1, 1, 2, 4, 3, 9, 4, 16. Maybe we double them. Maybe we divide them by 2, all that kind of stuff. So, number 5. Oh, I need the graph paper, though. Give me that. Get rid of that. Aha. Okay, number 5. R of x equals 4x squared minus 16. So good, this one actually will fit on my graph, and I learned my lesson. So I'm going to shift downward 16 units from the origin. Okay, I'm going to begin with that portion. So down 16 all the way down there. Okay. Sorry that you can't see it with a shot of me at the same time of this. Hopefully I haven't been covering anything else. I sometimes don't remember to look back at what I'm actually doing there. I'll keep it right at the bottom, right there. 4x squared, it's a vertical stretch by a factor of 4, which does mean that instead of going 1, 1, 2, 4, 3, 9, etc., we got to multiply those heights by 4. So over 1 up 4. 1, 2, 3, 4. Over 2 up 16. 4 times 4. So we're going to be quadrupling that, which actually brings me to the x-axis there. Over 3, we'd go up 36. I cannot fit that. It's actually pretty close, but I can't fit that. But 9 times 4 would be 36. And which also means if I'm graphing this and I'm being particular, if I actually wanted to graph, I technically shouldn't, so I'll tell you this, I technically shouldn't cross x equals negative 3 or x equals positive 3 right there because I never actually hit that point. So I'm going to slowly go, it gets really close, but I'm going to slowly get to here to start. There we go. Good enough. And then I'm going to go ahead and curve it. Work it downwards some more until it's the U shape. These vertical ones are not, I'm not a fan of the vertical ones. Like the vertical ones, the vertically stretched ones that are very tall. It's very hard to do on this. On a piece of paper, I'm a lot better. This stuff, no, absolutely not. It's never actually fully vertical. It just works out the way that it does like that. So, wow, very tall. Okay, this was a vertical stretch. Now, as much as I shifted down 16 first, I still have to explain A first, because that's technically what happens first. Vertically stretched by a factor of 4. And then we translated 16 units down. Okay, sorry about the handwriting mess. Let's go. Number 6. B of, oh, well, this is tall. B of x equals 8x squared. Number 6. B of x equals 8x squared. To be fair, I'm only going to fit one set of points. I'm only going to be able to fit one set of points given my graph stuff. I'm not changing scales here. So this does not vertically, this does not translate. The vertex is at the origin. And over 1 up 1 times 8 is 8. Over 2 up 4 times 8 is 32. You can't fit it. So, sorry. You give me this kind of problem. You ask a silly question, you get a silly answer. That's my motto. So this is extremely tall. Just vertically stretched by such a large factor. Arrows and all. The tip of my stylus is getting a little scratchy. Vertically stretched by a factor of 8. That's it and that's all. Vertically stretch by a factor of 8. Okay. That's number 6. Number 7. G of x equals 2/5 x squared. An interesting fraction indeed. I'll go with it as best as I can. with you guys understanding as best as we're able to. Number 7, g of x equals 2/5 x squared. Once again, the vertex is at the origin, but now we multiply all of our things by 2/5. You're just going to have to bear with me on the numbers. They're not fantastic. One number is going to be fine. That's when we go 5 over. That should be good. If you go over 1, we're going to go up 2/5 of 1. That's 2/5, around 0.4. We'll keep the points a little small here. When you go over 2, we're going to go up 2/5 of 4, which is 8/5, which is 1 3/5, so kind of like that. Over 3, up 2/5 of 9, which is 18/5, which is 3 3/5. So here. Over 4, up 2/5 of 16, which is 32/5, which is 6 2/5. 4, 5, 6 2/5. Now the good point right here is over 5, we're going to go up 2/5 of 25, which is 10. Right? It's 50/5. So that's 10. So this is going to be the nice point right here. I'm really going to highlight that one. 6, this is probably the last one I can fit. 36 times 2, 72/5, which is 18. Oh, that go, no. 14 2/5. So, like that. Oh, too far. So like that. Okay. It's a great looking graph once you get the points. Much better than 8x squared. This is going to be a much more beautiful looking curve. But to get those points, you're probably, once again, you're either probably going to change your scale and get something with just integer values. Like when you go over 10, you'd go up 40, things like that. But that's the one for sure that you'd be hitting and trying to make that curve as good as it couldn't look. And that's number 7. I like it though. Oh, vertically compressed. This one's not stretched. I believe the book will say shrink, but you vertically compress by a factor of 2/5. Anything that's less than 1 is a vertical compression, as by positive and negative standards. And number 8. This is 3 things I need to mention in its translation. I can already tell. Maybe you can as well. F of x. Whoops. Number 8. F of x equal, m of x. Pardon me. Equals negative 1/2 x squared minus 4. All right. 4 units down. Boom. Negative means it'll go downward, reflection over the x-axis, that kind of thing. And the 1/2 means take half of 1, 4, 9, 16, etc. So over 1, down half of 1. Over 2, down half of 4. Over 3, down half of 9. That's 4.5. Over 4, down half of 16. That's 8. Over 5, down half of 25. That's 12.5. And I'll be at negative 16.5, like that. Boom, boom, boom. So I'm going to reflect those points over here and give myself a nice looking graph. Hopefully you can follow up. Get something just as good looking. Maybe even better. Again, I plot what I can fit and I avoid table usage where I can. I still got the same graph as anybody else. So there's that graph. And this was a few things. Reflect over the x-axis. That's the negative portion. Reflect over x-axis. It's a vertical compression. That's the 1/2. Vertically compress or shrink by factor of 1/2. And don't say negative 1/2. The 1/2, the negative already did the thing in the reflection, right? And then you translate 4 units down. You vertically translate, but if you say down, I think that applies. You translate 4 units down. Okay, those were some things where we had to do graphs. Those ones take a while. Hopefully we're going to get off graphs now. A little bit, depending on what we're doing. Describe the transformation from the graph of f to the graph of g, then graph f and g in the same coordinate plane. All right, well, I just asked them to do less, and they said, no, we're going to double up your things. Do both of them this time. So I shouldn't speak my mind. Numbers 9 through 12. Half the problems, well, no, 2/3 of the problems. F of x equals 2x squared plus 1. G of x equals f of x plus 2. I remember these question types. Okay, so I'm going to do one in black, one in blue. F of x equals 2x squared plus 1. Now, g of x being, I'm going to do some work here. G of x being f of x plus 2. That means that we're going to take what f of x was, 2x squared plus 1, and we will add 2 to it. Now 1 plus 2 is 3. So g of x's equation in terms of x is 2x squared plus 3, which is actually something that they needed us to do. And we're going to do that right now. You can do it whichever way you want as far as when you end up doing the graph. They're saying take your function, this graph here, and make everything 2 taller, which is another way of working it out. Or just take both equations and kind of do it that way. So, and then we're going to describe that. Now, as far as the description goes, I think it's fair to say that we should probably talk about that right there, that we are translating f 2 units up to make g. Translate f of x 2 units upward. Right, that's what makes g's graph. Now, f of x is its own, it's not just the x squared graph, it's 2x squared plus 1. So it is translated up already, a unit right there. Over 1 up 2, right, 2 times 1. Over 2 up 8. So, bam, bam. And over 3 up 18, 9 times 2. I'm not going to be able to fit that one, so I'm just going to go and save it that there. Yeah, I'll just leave that. This next one is just 2 units upward. So this would be, let's draw the curve first. Now I'm not going to draw it in full. I'm just going to go kind of just like that, if that's okay. Just because I can't fit those other points, and it's going to kind of get in the way of the others if I do. Now this one's 2 units up, right? 2x squared plus 3. So right here. So over 1 up 2. Over 2 up 8. From 3 is 11, like that. And again, that's all I'm going to be able to fit on this one as well. So everything's 2 units upward from this one in black here. And yeah, it's just the black graph upward by 2 units, and that's it. I mean, that's it. That was a whole problem. But 2 graphs. There you go. I could do a copy and paste job. I'm going to do what you would probably have to do on the same problem. Kind of tough to do with just a pencil, though. So use 2 different colors if you can, is my recommendation. Number 10. We'll do f of x equals negative 3x squared plus 12. Yeah, I'm so glad that I learned my lesson about the doing the tall graphs. I don't know. Did I do tall graphs at the time of these in 3.2? I hope. G of x equals f of x minus 9. Okay. So, once again, description-wise, we're going to translate f 9 units downward to make g. That's going to be something I'm going to describe, but in order to see its actual form, let's take negative 3x squared plus 12, and let's subtract 9 from it. Boom, like that. So this will be negative 3x squared plus 3 as its simplified version of the equation, whereas I can just see what I'm going to do there. I can also take f and go 9 units downward. So we will be translating f of x 9 units downward. That's the description from from f to g. All right, so negative 3x squared plus 12. So we are going to shift up 12 units. This is our vertex. Negative means we're going to be flipped over. Over 1, down 3. Let's triple our heights. 1 times 3 here. Over 2, down 4 times 3. So that'll be at the, not the origin, but at the x-axis. And 9 times 3 being 27. 12 plus 17. This can fit. So I can fit it down at negative 15 here. I can fit it right here. Not the next one when I go 9 units downward, but this one I absolutely can, which if I can fit it, I will. So this guy is going to look like, I'm trying to be precise here. Okay, like this. And then on this side, the same effect. Boom, 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 boom. I'm going to make sure G's graph goes at least as low based on appearance. But I won't be able to fit the third set of points. So 9 units downward is at plus 3. See, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's where that plus 3 also exists there. Almost 3 units up, right? But now we do the same thing here. 1 down 3 over 2 down 12. So that's at, I can't do it. 3 minus 12 is negative 9. So right there. And again, that's all I can fit. I can't go 27 down, but I can at least draw this as low as the other graph that you see there. So Kind of like that. Remember, these graphs go forever. But regarding my window, that's what I got. Okay, number 10 is in the books. Let's go to number 11. Hold on, I'm curious. Oh, commercial. All right, f of x. F of x equals 1/2 x squared minus 2. And now we have g of x equals f of x minus 6. So once again, it's another translation. All these look to be just translations only because it's just the plus c concept. So we're going to take our f of x, our 1/2 x squared minus 2, and we will subtract 6 from that. And negative 2 minus 6 is negative 8. So 1/2 x squared minus 8. This graph goes upward. Excuse me, the graph faces upward, but we translate downward to begin with, both of them. And it is vertically compressed. They should be good-looking graphs, at least. They shouldn't really be in each other's way. I do like that. So let's take a look at this. F of x equals 1/2 x squared minus 2. So start at negative 2 on the y-axis there. It's just a vertical translation. Over 1, up half of 1. Over 2, up half of 4. Over 3, up half of 9. Over 4, up half of 8. I'm trying to do a quick count here. Up half of 25. That's 12.5 up. Over 6, up half of 36. You betcha, I can hit 16. 16 isn't half of 36. 18 is half of 36. But we started 2 down. So 18 minus 2. I'm doing 18 up from there. This is going to be a beautiful, splendid looking graph. And I'm hoping I can fit even another point for the green one. I want to get this one tall. I want things to look good. I want this to be the thumbnail of my video. Oh, absolutely. In fact, I will make this the thumbnail of my video. Just this guy right here. I don't ever do that thing. I just choose the thumbnail that they recommend for me. They're like, hey, here's a thumbnail. And I go, great, choose it. I used to try and do thumbnail things. It took way too long to just be working that out all day. I ain't about that life no more. I don't have enough time. All right. This thing's going to translate 6 units down, right? So 1, 2, 3, 4, 5, 6. What y value are we at right now? Negative 8. That's where that is. So everything else is the same. I could copy paste, but I'm just going to work this out again. 1, 1/2, 2, 2, 3, 4.5. That's half of 9. Now we'll go half of 8. That'll be on the x-axis. Let's reflect those to begin with and make sure we're in good company to start. We'll keep proceeding forward. 5, half of 25 is 12.5. So 12.5 from that is 4.5, I think. Like that. Let's keep reflecting now. Half of 36 is 18. So that'll be 18 up from negative 8 is 10. So right there. Let's see if we can fit a 7th. I'm intrigued. Half of 49 is 24.5. 24.5 from negative 8 is 16.5. Yes, we can fit it because this graph goes up to 17. So 16.5 right there. Remember, this one will never hit that one, right? It's not going to interfere or intersect or whatever. This is always it's a translated graph. This one's translated some units downward. It might appear like it's going to hit, but I promise you it ain't. They just go sharper together, so they'll probably just look closer. They'll have closer space between each other. But black always stays within green because it's just a translated. Technically, green's a translated graph of black. Okay, man, that one is looking beautiful. Let's write here. We're going to say translate f of x 6 units downward to make that good old G graph. That's looking quite good right there. You guys ready for the thumbnail with Braves in the background? All right, there it is. That'll be our thumbnail for the day. All right, cool. Okay, let's keep going forward. That's so beautiful. That's so good. All right, number 12. This one won't look as good. It's just going to be so tall. That's so tall. Good thing we got that one. F of x equals 5x squared minus 3. And then g of x equals f of x plus 1. Oh my gosh, this is going to look so crowded. It's only 1 unit up more. It's only translated 1, and this is so sharp. So this one was Imagine, this one was 6 units down, good separation, and was wider. This is going to be super tall and 1 unit within. This is going to be it's not a good problem. I mean, it's a fine problem. It's just, it's not separated enough. They have to give people separation. All right, let's begin with the, just this part. F of x is 5x squared minus 3. I might have to respond to an email again. I'll wait on it. This is going to give me 5x squared minus 2, because negative 3 plus 1 is negative 2. So there's that guy. From negative 3 to negative 2, translate 1 unit upward. Let's just write that. Translate f of x 1 unit up. And let's see what f of x looks like here, shall we? Negative 3, vertical translation. Boom. Over 1 up 5. Over 2 up, I can fit only one more point, and I can fit it. Over 2 up 4 times 5, which is 20, which is at 17, because 20 minus 3 is 17. So I can actually literally fit it right there. They know my graph axes, don't they? They knew I could fit it. Okay, now I need to kind of curve pretty nicely just to fit green within there. If I want another thumbnail, there's going to be one with like a thumbs down, like, this is too skinny. All right, green starts at negative 2, right? It's just 1 unit upward. So over 1 up 5, boom, boom. Hey, technically they're not intersecting. And then this is at this right here. It might look cool, but it doesn't look, like it might look like a 3D effect or something. I have no idea. See, it looks like it's just overrunning it now because I can't stay within it well enough. Oh my gosh, that one's not good. Nope, it might not look cool. If you go to a graphing calculator, hopefully you'll see more separation, but not much. Just kind of looks like two things, like, All right, so that's number 12. All right, we got a graph. Okay, at least these graphs are different now. Now we're on 3.3. So this is your ax squared plus bx plus c material. I'll just go to a new page. Numbers 13 through 16, graph the function, describe the domain and range. So I'm actually going to move these graphs over to the right this time. So on number 13, we're going to have f of x equals negative 4x squared minus 4x plus 7. We have to find the vertex of this thing to get things started. This is still your a value, like a vertical stretch factor would be, and a reflection and stuff. That doesn't change. And this actually is your y-intercept. So if I point out some things here, this is once again still your vertical stretch factor. And this guy here is your y-intercept. Those are already points that we can use. I'm even going to draw the axis of symmetry because I can get a point that reflects across there. But I'm going to plot everything that I can fit anyway. So your vertex here, the x value is at negative b over 2a. We're going to do negative, and your b is negative 4, over 2 times a, which is also negative 4. So this is going to be 4 over negative 8, which is negative 1/2. Now, it's not the easiest one to plot a lot of new points from. That's why that y-intercept is so good to have. The y value for your vertex is, you got to substitute negative 1/2 in for for x now to get y. So it's negative 4 times negative 1/2 quantity squared minus 4 times negative 1/2 plus 7. And if you recall, some nice things pan out when you add the first two things together. 4, that's a 2, and then plus 7. Actually, these calculate pretty cleanly anyway. So this is negative 1 plus 2 plus 7. Negative 1 plus 2 is positive 1. Remember, this switches. These two combine to become the positive version of that number. So positive 1 plus 7, which is 8. It's a lot more than I probably needed to write. I could have probably gone straight from there to 8, but that's okay. So your vertex is at negative 1/2, comma 8. Okay, that's where we're going to begin this graph. And it will go upside down. So negative 1/2, comma 8. There. So this 7, it's really close, right? The negative 1/2, that doesn't give you much separation from the y-intercept. So I am glad that I'm going to be getting more points myself. But the axis of symmetry is this line right here. So that might help me find more points to reflect. Because remember, my axis of symmetry in every other problem from here, besides 1 and 2, which were already graphed. But with me graphing, the axis of symmetry was always on the y-axis. So I didn't really need to draw it. It was kind of just there. But this one is nice to draw here. Now 0, 7 is actually a point that's on this graph, which also means that negative 1, comma 7 is also a point that's on this graph. They reflect across. That's not a point I would have gotten myself because it's not 1 away. 1 away goes at 1/2 here. And I go down 4. 1, 2, 3, 4 from here. So I'm going to plot a bunch of points that aren't really on. They're on the halves. They're on the halves here. 2 away, 1, 2. I'm going to go down 16. 16 down from, what was this, 8? 16 down from 8 is negative 8. So all the way down here. I can't see my points. Okay, right there. And then 1, 1, 2 away, 1, 2 away like that. I think that's all I can fit. I know that's all I can fit. But that's going to be this graph here. And we'll get to the domain and range next. Okay. I'm just going to stop the arrows right there. Pretty good points. Now, the y-intercept was helpful. It actually got me a third set of points. But they were so very close to the axis of symmetry. I kind of wish they were more separated to build the character. And even land on them myself. Okay. As far as domain and range goes, these domains should be all real numbers until we hit maybe word problems. But we're going to have an all real number domain. The range is going to be based on this being a maximum at 8. This is going to be y is less than or equal to 8. There's your domain. There's your range. There is your number 13. I'm trying to look ahead if we have to graph the rest of the way. We might not have to graph the rest of the way unless the word problems necessitate that we solve something, if that makes sense. We might have to solve by graphing. Number 14. Number 14, we have f of x equals 2x squared plus 12x plus 5. Same stuff. Did I start from talking about vertex? Yeah. So the vertex, we're going to get an x value of negative b over 2a, negative 12 over 2 times 2. At least this will be an integer, which is negative 12 over 4, which is negative 3. The y value, by doing f of negative 3, will be 2 times negative 3 squared plus 12 times negative 3 plus 5. Negative 3 squared is 9 times 2 is 18. And then minus 36, remember this will give us negative 18 plus 5. Negative 18 plus 5 is negative 13. That's a lot less work written. So the vertex is at negative 3, negative 13. And I'm going to start with that part on my graph. Where does it go from there? It goes upward? Okay. So, negative 3, negative 13. It's down here. And listen, there's a vertical stretch factor of 2. That's what that's all about. At some point, I'm going to hit 0, 5. So I'm going to put that right now. And there's another point that I can also reflect across now if I recognize this axis of symmetry. Not a required drawing, but something that is going to be helpful. This is 3 points away, and 3 points away on the other side, I have negative 6, 5. So those are for sure points. I'm going to hit them myself anyway, but let's go ahead and see that. Let's confirm that. Over 1 up 2, doubled my 1. Let's double 4 now and get 8. So 5, 6, 7, 8. That's at negative 5. And then over 3 up 9 times 2, which is 18. What's 18 up from negative 13? 5. Boom, that one and that one. Can I do 32 up? This is negative 13 plus 32 is, I don't know why I can't do these calculations. Well, 19. I can't fit that one, so I'm going to leave it like this. These days I have a lot of trouble with addition and subtraction for whatever reason. I'm always really good at multiplication. Okay. There's that graph, sort of. I'm kind of rough looking. The domain is all real numbers. The range, this has a minimum at negative 13. Its y is greater than or equal to negative 13. There you go. Number 15. Y equals x squared plus 4x minus 5. Oh, this is going to be a nice little graph. Thank you. Y equals x squared plus 4x minus 5. The vertex x value is at negative b over 2a. Remember your a is 1, 1x squared. Boom, just like that. Which is negative 4 over 2, which is negative 2 for x. The y values by doing f of negative 2, which is negative 2 squared, plus 4 times negative 2 minus 5. That'll be 4 minus 8, which is negative 4, minus 5, which is negative 9. So we'll have a vertex at negative 2, negative 9. Let's graph it. This is a 1x squared graph, so I get to do my 1, 1, 2, 4 just as standard as I would like to. So negative 2, negative 9 is right here. I have an axis of symmetry right here. Here we go. 1, oh, wait, by the way, y-intercept of negative 5. I'm going to hit that. 1, 1, boom. 2, 4, there it is, boom. 3, 9, we actually hit the x-axis there. 4, 16, what's 7 up from there? 7 up from 9. And 5, 25. 25 up from negative 9 is 16. Let's fit it. Yes. Yes. That one's good. Might be easier than the other ones. Especially, I mean, the first one we did is the hardest one. It had a fraction x and stuff. They really should probably grow and develop into more difficult problems as you're reviewing. I don't know. I won't tell them how to do their things. Sorry about my curve looking a little wonky. I swear on paper I'd be so much better looking than that. Just this is really hard to kind of take care of. The domain, all real numbers. The range, y is greater than or equal to negative 9 as it goes upward. There's your domain, there's your range, there's your answer, there's your graph. Looking good. One more of those ones, number 16. We're probably nearing its end, depending on how long the word problems go. Y equals negative 3x squared plus 6x plus 9. Okay, the vertex x value is at negative b over 2a. So that's negative 6 over negative 6, which is positive 1. So f of 1, or y, well, it says y equals, but that's okay. F of 1, I guess the last problem said it too. Negative 3 times 1 squared, that's negative 3, plus 6 times 1, that's 6, plus 9. Negative 3 plus 6 is positive 3, plus 9 is positive 12, and this will go upside down. So we have a vertex at 1, comma 12. Let's go. So go upside down, or reflected. 1, comma 12, here. Axis of symmetry at x equals 1, here. Vertical stretch of 3 is where we are flipped over, 1, 3. And, oh, by the way, y-intercept of 9. I just hit it. Y-intercept of 9, reflected. 2, 12. Hits the x-axis. That's 12 down from 12. And 3, 27. 12, yeah, negative 15. So I can hit that. Right down there. And my final curve for this set. Maybe my final graph. You and I both look forward to that, right? Okay. Okay. Domain is all real numbers. Range is y is less than or equal to 12. Great. Okay. There are the graphs with domains and ranges. Number 17 through 20. Tell whether the function has a minimum value or a maximum value. Then find the value. So on these problems, we are determining whether the graph faces up. We're not going to graph it, but just determine whether the graph faces upward or downward based on the sign of A. This is positive. Therefore, the graph would face this way upward. Therefore, it has a minimum. Graph has a minimum when it faces upward. So there is a minimum. It says state whether it has a minimum or maximum. This has a minimum. And I'm going to figure out what that is in a second by finding the value. The value is the y value of the vertex. To find the y, we need the x. So for the vertex, the x value is negative b over 2a, which is negative 10 over 10, which is negative 1. At x equals negative 1, we will have a minimum of y equals bleh, right? We'll find out what it is. F of negative 1 is 5 times negative 1 quantity squared plus 10 times negative 1 minus 3. Negative 1 squared is 1 times 5 is 5. Minus 10 is negative 5. Minus 3 is negative 8. So we have a minimum of negative 8. That's the vertex y portion of the value. That is the answer there. Again, vertex is at negative 1, negative 8. The minimum is at negative 8. We proceed forward. So unless they pose some challenging problems with the fractions and such, which this might be, then we'll see how it goes. Number 18. F of x equals negative 1/2 x squared plus 2x plus 16. This graph goes upside down. Therefore, its vertex represents the maximum. And that's exactly what this thing has. It has a maximum here. What is that maximum? Let's find out the x value of the vertex. To find the y, the x is negative b over 2a, like so. That's negative 2 divided by 2 times negative 1/2 is negative 1. So that's positive 2 for the x. But the y, f of 2, we got to do negative 1/2 times 2 squared plus 2 times 2 plus 16. 2 squared is 4 times negative 1/2 is negative 2. Plus 4 is positive 2. Plus 16 is 18. 18 represents your maximum value. It's the y value where we peak out. Vertex 2, 18. That's the top. Two more of those. Number 19. I think that were hard. There were some pretty hard ones we had in the actual section when we were working on these. So these are actually favorable. Y equals negative x squared plus 4x plus 12. This is going to once again be a maximum, given that x squared is negative, a negative 1. So the vertex x value is negative b over 2a. That a is negative 1. Negative 4 over negative 2 is positive 2, just like last time. But of course, this is a different equation. So let's see what f of negative 1 is all about. I don't know why I said negative 1. I was looking at the a value. Let's see what f of 2 is all about. How about that? Negative 2 squared plus 4 times 2 plus 12. Now, be careful here. The negative sits outside of the 2. I'm not squaring negative 2. I'm squaring 2. And then I turn that negative. So 2 squared is 4. And that turns into negative 4. And then plus 8 is positive 4. Remember, that should always happen on that vertex section. It should kind of flip its sign. And 4 plus 12 is 16. 16 is the maximum. 2, 16 is the vertex. The maximum occurs at y equals 16. And finally, number 20. Not finally, but from this section, number 20. We have y equals 2x squared plus 8x plus 3. This will feature a minimum, given that this is a positive 2 here. The a value is positive. So the vertex x value is going to be at negative 8 over 2 times 2, negative b over 2a. Negative 8 over 4 is negative 2. And we are going to be taking f of negative 2. Substitute negative 2 for x. Figure out your y. 2 times negative 2 squared plus 8 times negative 2 plus 3. Negative 2 squared is 4 times 2 is 8. Minus 16 is negative 8. Plus 3 is negative 5. This has a minimum. Negative 5 is said minimum. We are done. Ooh, hand cramp on that. Just writing that pretty fast. Okay, 3 more questions. Look like there's some form of word problem. Start with number 21. The distance y in feet that a coconut falls after t seconds is given by the function y equals 16 t squared. Use a graph to determine how many seconds it takes for the coconut to fall 64 feet. Okay. It says use a graph, so we will graph, and I'm fine with that. So here's the thing. Y equals 16t squared. It's a little interesting with the way they talk about the problem, because normally you'd see a negative 16t squared. We look at an upside-down graph talking about parabola is gravity, and it's falling. But this time they're saying the distance it falls from the tree, the distance that it falls in general. So, when t equals 1, right, 1 squared is 1 times 16 is 16. The coconut fell 16 feet, but we're going to see a parabola that goes upward. It's not falling upward. It's just showing the distance that it's traveled. So your y is just distance. not the actual height. Hopefully that makes sense. Now, y equals 16t squared. Y is the height in feet, or the distance in feet. And they're asking how many seconds will it take to fall 64 feet, which I guess we're assuming that it's at least 64 feet in the air. So we're going to set y equal to 64 as well. Now, there are two different versions of what you can do here. Number one is graphing these two, graphing y equals 16t squared and graphing y equals 64, and then determining when 16t squared equals 64 and finding those t values. Number two is setting these equal to each other, 16t squared equals 64, subtracting 64 over, and then finding out when this graph shifted downward hits the x-axis or the t-axis, which is maybe the one that they want. It doesn't matter. You're going to get the same answer. One is just 64 units shifted downward. One stays at the origin, but you have a y equals 64 line upward. They're both the same thing. Since they said use a graph, we do have to graph this. We can't solve using factoring and difference of two squares and stuff. We could confirm it, but we're just going to go and stick with this. So I have to change my scales, my graph naturally, or we don't actually have scales to begin with, but let's go ahead and go down by 20s. So negative 20, negative 40, negative 60, which does mean that these points are going, every one of these is a 4, which is kind of nice because negative 64, 16t squared minus 64 equals 0. We got to find out when do we hit x-axis, or in this case, t-axis. That's just when do we hit this? When does this line actually hit? What values of t? T. So what's nice is this y equals, basically graph y equals this is shifted down 64 units. So that's a 4 right there, 64. Now 1 is going to look kind of dumb. So I'm going to go 2, and these are still going. This is 5, and this is negative 5 like that. So this is 2, 4, right? Before it was at 64, etc. 3, 9 is weird. 4, 16. 16 like this. So this is going to be kind of nice. 5, 25, nah. 6, 36. 36, 5, and 4 is 9. So 5, 6, 7, 8, 9. See, I'm not dividing the ones by 4 that are kind of... I'm dividing by 4 because my scale is 4 times larger. What was that? 6, 7, 49 over 4, no. 8, 64 over 4 is 16. And this is where it actually comes up to hit this right here. Boom. And boom. So I'm using a graph to confirm that. Whether I'm shifted 64 units down or kept where I was in the blue line there is at y equals 64. This will be the same style graph, assuming you keep the scale that I do. Now I'm just going to go ahead and plot those ones. I can fit one more set. I'm going to keep going. At 10... 100 over that is 25, and 25 up from 16 is 9, so I'm going to be right there. We already found the ones that we needed, but they said graph, right? They said graph. Why not make it better looking? Okay, now these are the points I was looking for. When did I cross there? So those t values are t equals negative 7, no, negative 8, t equals negative 8, and t equals positive 8, or I should say or t equals positive 8. Now, the coconut didn't fall in negative time. It fell at time 0, so this one is going to be extraneous. That's not going to apply. T equals 8 will apply, and t is in seconds. So 8 seconds. It'll take 8 seconds for this coconut to fall 64 feet. Doesn't that sound long? I mean, I know gravity's a thing, but does that sound long? Is gravity that slow? Now that I think about it, 8 seconds for 64 feet, something seems off about that. Now that I think about it, that seems slow. Now that I think about it, I have to drop something 64 feet to think about it. Wow. Okay. Yeah. But anyway, so that's the answer. I don't know. Now I'm perplexed by that. I feel like it would take 4.5 seconds. I don't know. Interesting. Okay, number 22. The function y equals negative 16t squared plus 25 represents the height and feet of a pine cone t seconds after falling from a tree. So this is the same kind of thing. This time they're going to talk about the actual height. So this will be an upside down parabola. You're going to see it. Remember, this projectile outward means nothing but time going on. It's dropping straight down, but you're going to see an upside down graph. We're going to say after how many seconds does it hit the ground? Same kind of question as before. And then a second pine cone falls from a height of blah, blah, blah. We're going to take care of all that. So first we have y equals negative 16t squared plus 25. Now, I am curious actually about the second question. Oh, the second question I don't need to graph. The first question here we will graph it because it's kind of what they're asking us to do. They don't actually say it, but these sections are about graphing. Now, I can't fit 25 here unless I scale differently. So let's go by, I guess, 2s. So 10. This will be 10 and 20 and 30. Now, 25 is in between, so here's 25. And negative 16t squared I screwed up the last problem. 8 seconds, that did seem slow. I didn't account for, I just went over 1 up 4 and stuff. Guys, I botched this problem. I really apologize. I really did. No wonder that 8 seconds seemed really slow. I felt like it would be so much faster. So, oh my goodness. I'm not going to edit that out because I'm not about censorship. So, really apologize. I got to stretch by 16. So this will help answer both questions at once. Okay. 8 seconds was way too slow. Thankfully, when I double checked that, I saw the 16. I totally forgot about what we were doing with that after the 64. So, hey, over 1, up 16. So that's 1, 2, 3, 4 of these here. Over 2, up 16 times 4. 2 seconds sounds a lot better. 16 times 4 is 64. Okay, it hits it. I was being generous when I said the 4.5 seconds and stuff. I don't know how high 64 feet is, but 2 seconds later, it hits the ground. Boy, that makes a lot of sense. I'm going to go ahead and leave a nice old note on the bottom. You're going to have to check this description section. It's the very first thing I'm going to say. I'm going to say, keep watch at how I actually fix this thing. All right, t equals -2 or +2, and we can't be -2, so we're going to say 2 seconds. Okay. Something seemed so wrong in the last one. I really questioned gravity. I know I keep saying that, but I was really, during this problem as I was working on here, I kept tracking in my head. Here's 8 seconds. Ready and go. Time. 64 feet, it takes that long for a coconut to hit the ground. I think a feather would hit the ground faster. All right, let's go down 6 over 1, down 16. Now this one is, these go by 2s, right? So let's go down 8. 1, 2, 3, 4, 5, 6, 7, 8. I guess I should have said that's also 9 at 9. So here and here, and then over 2, down 4 times, so down 64. So 25 minus 64, 39. Now this is only going to hit 34 here, so I don't know if I can really fit it. It's going to be kind of like off, kind of like that-ish, but it's going to be about what we have. Now this my graph itself won't tell me exactly what it is, so I might have to solve this kind of more so by factoring. You know, I'm sure the book would say something like, oh, use a calculator and plug numbers in until it works. Now, I'm guessing it's probably at 1.5 and -1.5. So to actually solve, well, actually, I'm not positive. So to solve this thing, we would set this equal to 0. I guess I'm just going to actually solve it. We'd set this equal to 0. I'm going to, there's no GCF outside of the negative, but that's kind of helpful. It kind of sees this difference of 2 squares for me. So this thing factors into 4t minus 5 times 4t plus 5. Okay, it's not at 1.5. So you set these equal to 0. 4t minus 5 equals 0. 4t equals 5 and t equals 5/4. That's one answer. The other answer would have been -5/4, which will not apply. So we're going to go ahead and say nope. So it's going to be after 1.25 seconds. Like that. That's part A. So that's what we're hitting right there. That's this guy. Boom. I feel so bad about number 21. I'm so sorry about that. Yeah, 8 seconds is a long time for something to drop to the ground. Whew. Part B. A second pine cone falls from a height of 36 feet. Which pine cone hits the ground in the least amount of time? Explain. Well, 36 would be up here. I'm not going to draw the whole graph or anything, but 36 would be up here, and the same gravity is going to take longer, right? I mean, you can argue it logically. I'm sure they wanted you to talk about the graph stuff itself as well. So the second pine cone would take longer to hit the ground. Because it's higher up. Because it's higher up. And therefore, its T would be further separated from the vertex. I mean, this is something you could ask, a 4-year-old. I'm not saying it's a 4-year-old question. I'm saying if I explain it saying like, no, it would take longer to hit the ground because it's higher up. I mean, like, we know that. But as far as the graph thing goes, right, we're saying that it's separated out farther. It's only a translation. It's only vertically translated up, which means some other point over here is going to be hitting it in a different way, right? That's what we're doing. Okay, I'm glad I can answer 4-year-old questions, but I can't count to 16. All right, one more question, guys. Number 23. Number 23. The function shown models the height. So this function models the height in feet of a softball. Hey, this is my domain. Of a softball t seconds after it is pitched in an underhand motion. Now, this isn't necessarily, I want to remind you guys, this isn't necessarily the ball's arc. It could be, but this is time going by. Keep that in mind. This is time going by. So the height of a softball t seconds after it's pitched in an underhand motion. Describe the domain and range. Find the maximum height of the softball. Okay. So h of t equals negative 16t squared plus 32, plus 32t plus 2. Okay, now the graph, they kind of show you the graph as well, and I'm going to go ahead and copy and paste this guy right here. Let's see. Give me 1 second. Copy and, what's that? And paste. Okay, now if you can kind of see this graph, guys, take a look at this. Here are my axes, but look at where the parabola starts. It doesn't start at the origin, right? It starts right here. Now, how come? Well, because we're pitching it, right? We're pitching in an underhand motion. We're not pitching from the dirt. We're at our waist level or something like that. We're underhand. That height is the y-intercept. The y-intercept. And this is important because this domain, guys, listen, the domain's not all real numbers. Once I release the ball, then the arc is demonstrated. There's the model. That's at time 0. This is where this thing starts height-wise, and this is where the domain begins as well. That doesn't mean that this accounts for the range or anything, but this is where this graph starts at 2. And then it hits some top, and then it actually does hit the ground, which they ask to find the maximum height. They don't say when it hits the ground. But it does hit the ground eventually. That height ends up being 0, and we do hit a maximum height here, which we got to figure out. But the y-intercept is at 0, 2. That's actually where it, hopefully you can kind of see that too. That's where it goes there. Okay. Now, regarding domain, the domain, oh, you know what? I do need to know where it hits the ground for the domain. I need to know the end point. This goes from 0 to t to some ending. What is that ending? I got to figure that out. I have to find out when this thing hits 0. Now, I'm actually, this time, because I don't have the scale of the graph and they just kind of give me this, I'm more inclined this time, if you don't mind, for me to solve this thing algebraically. I have to actually figure out where this hits. I'm sure that the book probably says, I used a graphing calculator and found out where it intersected. So I'm going to go ahead and just do this one algebraically. If you'd like to use a calculator, go ahead. This one's probably less in the form of the graph thing itself. So set equal to 0. I have a GCF of negative 2, and if I factor that out, I have 8t squared minus 16t minus 1. It's not a perfect square trinomial. This is not factorable. Okay, so this one's not factorable. So I think they probably do want you to use a graphing calculator then in this case if this happens. Because there's a way to solve this using what's called quadratic formula or completing the square. That's all in chapter 4 though. This one on the other hand though is not factorable. So let's go ahead, let me pop up my graphing calculator. So this is really one of those understand the problem kinds of questions, right? We understand the problem. So let me pop this up. Give me 1 second. I didn't have it prepared. Okay, now I am. There we go. All right, so we're going to do the original. We're going to do negative 16 t squared plus 32t, or x. I have to use x here, plus 2. Now, if you want to look at the graph, it's not quite the same window range. Let me try and get the same window range that they'd probably have. Let's go from like, I don't know how far it goes. It didn't look like it went very far, right? Time-wise, let's go to 5, and let's stretch that y quite a bit. Let's go 40 feet just in case and just see the curve for what it is. Like that, right? Was that factorable? Did that hit 2? Did I write something wrong? Let's see. Value. Let's see the zeros. Let's see the zeros. Left bound, right bound. No, it didn't hit 2. Okay, I was going to say something's way wrong there. 2.0606602. Now that's that t value right there. That's t is about 2.06. I was going to say, or 1, I'm going to round there, seconds. I don't know who's using a stopwatch with 3. No one uses a stopwatch with thousandths of a second. I'm going to 2.06. So that's what this is here. 2.06. You actually had to find out where it hits the ground, and it's going to be there. Graphing calculator confirms. Use quadratic formula. Oh, you can't see what I'm writing. If you can't use quadratic formula or completing the square because you haven't learned it yet, because we do chapter 3 before chapter 4, then yeah, use the graphing calculator just like that. Okay, the range is going to be based off the maximum height. So this is kind of interesting. They said describe the domain and range. They didn't say find it. I'm still going to find it anyway. I'll describe it afterward. Okay, I'll find it. I'll do that. So I was going to say, if they said find the domain and range, which it sounds like we don't have to do, I would have had to have found when it hits the ground and the maximum height to begin with. So I'll describe them afterwards, if you don't mind. Well, let's describe them now. So the domain is the time that the softball is in the air. The range is the lowest to highest ground. Let's see, ground to highest peak heights of the softball. So that's the description. Let's actually find that range by finding that other part. What's the maximum height? That's another part that they asked. So the maximum height, we're going to take negative 16t squared plus 32t plus 2. And let's do our negative b over 2a stuff. So for vertex, the t value is negative b over 2a, which is negative 32 over negative 32, which is 1. It takes 1 second to reach its maximum height, but what is that maximum height? Let's do h of 1. Negative 16 times 1 squared plus 32 times 1 plus 2, which is negative 16 plus 32, which is 16 plus 2, which is 18. 18 feet. Max height, 18 feet. Okay. As far as range goes, the lowest height it hits is 0 when it hits the ground. The highest height it hits is 18. Once again, they said describe them. This would have been in seconds. This would have been in feet. And they said describe them. They didn't say find them. I gave you a little bit extra there. I said you had to use a graphing calculator to find that, but that helps describe it at least, and we check that out. All right, guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. I'm going to go and finish there. See you in the next one, which will be section 3.4, where we graph, I believe, out of vertex form. Your personal favorite, my personal favorite. Let's go get them. Take care. See you then.